Hello everyone, welcome to recitation number 10, and we've hit double digits, so that's cool. So for today we're going to be talking more on decidability, so solving more questions there, then we'll introduce undecidable problems, and we'll talk about reducibility. So what is that? What's the meaning of it? So we're going to be starting off with these decidable problems. So we did see these last time. Hopefully you try to look at them, maybe solve them. And we're actually going to be starting not with the first one, with 4.12. So let A be this language. It'll accept M if M is a DFA that doesn't accept any string containing an odd number of ones. We need to show that A is decidable, but again, it'll accept DFA's M such that this machine doesn't accept any string containing an odd number of ones. So the end goal is to reach some machine. So in order to prove that this is a decidable problem, we have to build some machine. We can call it X. It takes as input M, such that M is a DFA, and tell me either yes or no if it doesn't accept or accepts. So it'll say yes when what? When this. The machine M doesn't accept any string containing an odd number of ones. Now, last time we assumed the following. We assumed that we have the machine EQDFA is already decidable, which means it's a machine that takes as input two things, or two DFAs, DFA-A and DFA-B, and it'll tell me yes or no if they have the same language. So yes, no, if the language of A is the same as B, and they're both DFAs. We also used a CFG, which is just a machine that takes a grammar G and the string W, and it'll tell you yes if G generates that W string, or no otherwise. Okay. Now, but for today, we're going to be assuming one more thing, which is the E DFA, and E starts for empty. It's simply the language where, there's some DFA-A. It'll tell me yes or no if that language is empty. So yes, if the language of A is nothing. All right, now for this first one, we're actually going to be trying to use, let's use this new machine, eDFA. So how do you want to do this? Well, last time we did a lot of just drawing, and we're going to be doing that too, but for this time, let's try to write as well, because we want to be able to express these machines. So what do we want to do here? Well, I want to use the fact that eDFA exists. That machine exists. So how would this one be helpful? Well, here's how we'll do it. Of course, feel free to pause anytime you see this and try to solve the problem yourself. But eDFA is gonna take some machine, some DFAA, and it's gonna check if its language is empty. So that would be useful if I do an intersection maybe between two things. So I'm going to be building the definition of X. On input M, such that M is a DFA, we're going to be doing the following. Let's create a new DFA. Nothing that's going to stop us from doing this. So one, create a DFA A such that the language of A is, this might seem weird, but like odd number of ones. Why do I want to do this? If I make a DFA that has the language of odd number of ones, I'm not saying it contains them, I think it's made up of only that. And that's not hard to see, right? We can draw this pretty quickly or easily. It's this machine. Whenever you do one, we go here, we go back here, and we'll accept if it's an odd number of ones. And if there's like a 0, 2, we can just self-loop on each loop. Okay, so that machine exists, not hard to draw. What we'll be doing next is create a DFA B such that the language of B is the language of A intersection with the language M. What's M? Remember, X as input is taking the DFA-M. Now I'm creating two more. A is the odd number of ones, and B is the intersection of both these language. Am I allowed to do the second part? Well, yeah. Remember, we were able to convert from NFA to DFA. Like, there's a sequence of steps that converts from an NFA to a DFA, and there's also a sequence of steps that will create a DFA. That's the intersection of two other DFAs. Okay, now comes the cool part. We're going to be running Turing machine T on input B, such that this Turing machine decides the language A, or sorry, the language E DFA. Very important that I say, oh, there's some Turing machine that runs the machine B. I'm not going to say that, oh, EQDFA or EDFA itself is going to be running it, because that's just the language. It's the machine that decides that language that we're going to be running. But what happens when what happens when I do that? Well, two things. Either this Turing machine is going to accept or reject. So if T accepts, or T might reject. But what does it mean if I accept or reject in this scenario? If T accepts, it's telling me that DFAB is empty. It's telling me that the intersection between both A and M is empty. So there's nothing in common between the machine that only accepts an odd number of ones and between the machine that we're trying to check if it does accept any odd number of ones. Okay, so drawing this. So it's easier to look at this in terms of sets. So imagine you have your universe and there's two sets. There's the language of M, and then there's the language of A. And we created A in a way that it only accepts odd strings, odd one strings. We made B that's the intersection of both of them, so it's this thing in the middle. And we fed it into the machine EDFA, and it's telling us, oh, it's empty. Like this thing that we have highlighted, it actually doesn't exist. So the actual scenario is you have the language of M on its own and the language of A on its own. So there's really nothing in common, which is cool. We just have to say now, what does our machine up there say? Well, X accepts, or we can just say right away accept, because this is the definition of the machine X. So if T accepts, we're going to be accepting too, since that means, oh, the language of B is empty. So the intersection is empty as well. Meaning there's nothing in common. So let's keep going. So like M doesn't accept odd number of ones. Okay. So that's if we accept, if T accepts, but if it rejects, well, we'll just reject. Because if T rejects, what does it mean? Oh, the intersection is not empty. So there is something in common. So there is some odd number of strings. It doesn't have to be all of them, but there are some odd number of one strings that M accepts. And that's it. Now, if we actually want to draw this, we'll do that. Okay. So remember, this big machine that we're trying to draw, which only takes, this is X, only takes as input M is a DFA. Inside, we did two things. We did really step 1 and 2 first, like we created some machine. Then we use the fact that EQDFA exists. So here we call it T decides EQDFA. Oh, EDFA, I keep seeing. You're gonna hear me say that a lot. I don't know why I keep confusing the two. So it's EDFA, the language that just checks if something is empty. So using one, we created DFAA, and here DFAB. And it was this one that we fed into our machine. And when this says yes, or accepts, so will we. If this says no, well, so will we. It doesn't always have to be the case that yes is followed by yes and no is followed by no. Sometimes like the wiring might be flipped, but in this case it's not. Okay, cool. I think that's everything for this first part. Now let's move on to the next one. Okay, so A is the language that takes a couple this time, R and S. They're both regular expressions and one is completely inside the other. So the language of R is completely inside of S. Show that A is decidable. Now the cool thing with these problems is there is no unique solution. You could come up with several solutions. And actually in class, we had two suggestions. One wanted to use the EDFA, like the new assumption that we took, and one wanted to use the old assumption EQDFA. And actually both work. So we'll be doing both as well. And you'll see like how very similar it is. Like even this writing that we have, you could almost literally copy paste it and just change a few things. So what are some of the things that we might be wanting to change? Okay. Well, first we're going to be taking the couple R and S, where R and S are just regular expressions. Now, let's say first we want to use actually EQDFA. So let's using EQDFA because that might be the easier one to understand. So we're going to need two inputs. We're going to need the two DFAs, essentially, DFAA and DFAB. But right now we have two rejects, so we're going to have to fix that. And what we're trying to prove, again, if we look at it in terms of sets, what we're trying to find is this scenario. You have S and you have R completely inside. There are other scenarios. There's the scenario where it's the opposite, where maybe S is completely in R. There's the case where there's nothing common between them. So R here, maybe S here. And finally, like the more general scenario where there's something, just some intersection between them. Not a bad idea to think of it in terms of sets. It'll make things easier. Cool. So we want this scenario. How can I get that? How can I prove that the language of R is complete in S? Well, one suggestion said, hey, how about I create a DFA for R? And then another one for what? So think about that. What do I want? So first of all, I'll create a DFA A such that the language of A is the language of R. And the other one is just going to be the intersection of both of them. So like this is the change we made here. Then we'll make another one, language B, such that it's the language of R intersection S. Why do I want to do that? Well, you have R and you have R intersection with S. What do you think will happen if we check if both of these are the same? Like if I'm checking if the language of R is the same as the language of R intersection with the language of S. Let's check all of the other scenarios. Here, the intersection, when it's the general case, it's just something in the middle. So the intersection is not all R. And here the intersection is like nothing. There's nothing in common. So the intersection is actually empty, which is not R. Here the intersection between R and S is S, which is also not R. If we're left with the scenario that we do care about, if I intersect S with R, I get R. So that's the scenario where, oh, if R is completely inside of S, then the intersection between both languages has to be just R. So that's why we're going with this. Now we'll run Turing machine T on B as well, such that T decides EQ DFA. And two scenarios, either T is going to accept or reject. If T accepts, like they're the same, as we just mentioned, if they're the same, then that means R has to be completely inside. So if T accepts, we'll accept. Since this means that the language, or R, the set R is completely, don't want the trademark, or whatever that is completely inside S. Otherwise, we reject, because if they're not the same, then we get one of these other scenarios. Either, oh, it's partially, or it's the other way around, S is completely there, or hey, there's nothing in between them. So we reject otherwise. So hopefully that made sense. Okay, and you can try to draw the machine yourself, and you'll get again something similar to the drawing of X here. Now let's try to do the same thing, but now we're going to be using EDFA. So how do we do that one? I really wish I didn't do that, because now I'm going to have to draw some things again. Actually, we'll just draw the case that we care about, first of all. So this time it's using EDFA. So the new idea. So unlike before where we gave it 2 DFAs, now I just want to give it 1. And what might I give it? So this isn't exactly like an QDFA, it's just something that decides it. So maybe T decides. Same thing here, T decides. I just want to make it clear so we don't confuse like the actual machines with the languages that they decide. Okay, let's see the scenario that we care about now. R is completely in S. Now, there were several suggestions. Again, it had to do with some sort of intersection. You can think about it, but for a few parts. Like, you can try to do the intersection again. That's not going to work, right? Like, because if I intersect S with R, I'm going to get R, which won't be empty. Again, we're going to try to create some machine that's going to be the intersection, or some sort of intersection between them. Maybe a union, but I'm not sure if union is going to work here. Okay, the intersection won't work. What are some other scenarios? How about the complement of S? What do you think is the complement of S? It's everything outside of S. What do you want to intersect that with? So the complement of S, if we try to intersect it with R, we're going to get nothing, right? For every scenario other than the one we care about, we're going to get nothing. Let's see this scenario. That's not, so the general scenario. what does the intersection give us? So we have, say, R and S. Everything outside of S, we're going to be intersecting with R. So this gets us R, which might help us in some scenario, but not in this case, because we're going to be using the machine EDFA. We really want the intersection to be empty, so it's helpful. Other scenario. They're completely empty, or there's nothing common between them. Oh, I actually made a mistake, I think, for the previous one. It's not all R going to be. Because it has to be the complement of S. So it's going to be some portion of R minus S. In this case, when there's nothing common between them, it's going to be all R. So this actually might be... Maybe this would be useful if you want to use it for the previous part for EQDFA. Because if you think about it, this is sort of the opposite scenario when it's completely inside, right? It's completely outside. So yeah, maybe there's something there. And then there's the opposite scenario. What if S is completely in R? Well, again, we're going to be getting some portion of R. So here it's R minus completely S. Before it was R minus a portion of S. Cool. Again, the scenario that we care about, it's the one that works. When you intersect the complement of S with all of R, you get nothing. Not sure how I'm going to get the bar there, so I'll just call it here. First of all, the language of A is going to be what? The language of R intersection with the language of complement of S. Do I need the other machine? No, so I'll actually leave this part empty. Don't need it. We're going to be using EDFA. So very important we differentiate every time. Here it happened to be, oh, here it changed here. Now what happens if T accepts and if T rejects? If T accepts, should we accept? T is telling us that, oh, the intersection between R and S complement is nothing. So yeah, we should accept. If T accepts, like there's nothing in common between these two, it means R has to be completely inside of S. So if T accepts, then that means R, like it's the same reasoning. And if T rejects, we reject too. Cool. Oh, I do actually need to fix this one. It's actually A that we're running, not B, because we don't have the machine B anymore. So hopefully you're able to see like how really similar it is. Like how, just like last time, we were like the drawings are almost the same here, even like the description is pretty similar. You're always taking some input. You might be creating some machines that you need. You're definitely going to be using some machine that you already know is decidable to build on top of it, and so on. Maybe not always, because eventually, because at some point somebody had to prove that EQDFA and EDFA, etc. Somebody had to prove that those were decidable, and maybe they didn't have a building block. So there's, I'm not saying this is the only way, but it's much easier when you build like on top of things that are already true. What about this one? So here the idea is going to be slightly different. Let infinite DFA, the language A, or the language that will accept A if A is a DFA, and L of A is an infinite language. So we're taking a DFA A and we'll accept only if it's infinite. Now that's kind of weird. How can we really prove that something's infinite? So for example, let's focus on, say, the language. So that's 0, 3K. Okay, so just the language that's multiple of 3 zeros. So this could have epsilon, could have 3 zeros, 6 zeros, etc., and so on. This is technically infinite. Like this should belong to my language. Like the DFA that decides this language or accepts this language, it should be in my bigger language, like infinite DFA. But how can we prove that? So first, let's see the idea. What really makes a language infinite? So if I want to draw this machine, so read a 0, read a 0, then if we read one more 0, we go all the way back, and the starting state is accepting. And this arrow that I drew, maybe that's the hint. So actually, some of you had an idea. Do I have some sort of loop, or am I revisiting the same state? What do I mean by that? Well, 0, 0, 0, this specific string. What's happening? So I'll name the states like Q1, Q2. Actually, let's call them Q0, Q1, Q2. Like programmers do that. So what's happening with the string 0, 0? I'm starting at Q0. I'm going then to Q1, going to Q2, then go all the way back to Q1, to Q0. And that's really the idea. You started at some state. You went on a journey, and then you ended up at that same state again. What's stopping you from repeating this as many times as you want? What's stopping me from then going again? Oh, Q1, then Q2, then Q0 again. Nothing. You can keep repeating this cycle as many times as you want, and that's the idea. If you have a loop, or in other words, if you revisit the same state, then that's it. You should accept. Now, easier said than done, because maybe this is the proof of an idea that you took in class. It's similar to the pumping lemma, almost. Maybe it has something to do with the pumping lemma. How can we actually prove that? Again, we want to use some of the previous machines. And actually, what we're going to be using is... So either EQDFA or DFA, right? We don't want to go with ACFG because there's no grammars here yet. Let's go with EDFA. Maybe the other one works too. Like, again, there's no unique solution. So we'll go with EDFA. So it's going to be a machine that takes a DFA and it's going to check it, it's empty. And the idea might be similar to before. Like this language, I want to intersect it with something, and hopefully that intersection will be something that's empty. So what could I intersect it with? Well, how can I actually ensure that I revisit the same state? So with 3 zeros, it did revisit the same state. Why? Well, we started at the Q0, we went here, then we went back. Is it the same thing for the empty string, like for epsilon? With epsilon, you start right away at Q0 and you accept, so you never revisit. With 6 zeros, you're going to revisit like twice. So you need a string that's big enough to ensure that you revisit the same state. Well, look at it. How many states do you have here? You have 3 states. 1, 2, 3. When do you revisit? Well, the string of length 1, not enough. Or of length 0, which is epsilon. The string of length 1 will not be enough because, oh, I read Q0, I go to Q1, that's also not enough. Of length 2, Q1, Q2, not enough. I need at least length 3, which is I go over here, then if I read something else, I have to go back. I need at least the length of length 3 to accept. Or in other words, I need it to be at least the same size as the number of states that I have. So if you have a string that's the same size, at least, of the number of states that you have, and you accept it, that means you must have visited at some point. So let's actually write that down. So if my DFA accepts string of length at least the same or the number of states in my DFA, that means there was some sort of loop, or in other words, we revisited the same state twice. Or we revisited some state. Which means our language is infinite. Okay, that's what we want to do here. Now, in this scenario, in this specific example, if I want to keep going, what could I do? Well, I'll create some DFA that accepts strings of at least length 0. How could I do that? Well, Q0 goes to Q1. Doesn't have to be like the same states as before. Goes to Q2, goes to Q3. Do you agree or not with this? And I'll make this one loop over itself, and I'll accept here. This is the DFA that accepts strings of length at least 3, no matter what they are. Like, if we go with the scenario, it's going to be like 0, 0, 0, if I only accept zeros. So this is accepting strings that are of at least size greater than or equal to 3. Like, if I want to make the language of this one, it's some number of zeros n such that n is greater than or equal to 3. And that's enough. Again, it doesn't have to be strictly bigger than the number of states. It actually, if it's equal, that's enough. Now, if I do the intersection between both of these, and the intersection is empty, what does that mean? Oh, your DFA A, it doesn't accept any strings of size greater than or equal to 3, so it can't be infinite. So that's sort of the idea. Now we're actually going to be doing the proof. Let's go ahead and let's get the big definition we wrote at the beginning and see how we can modify it. Okay, X on input, they call the machine A, and A is a DFA. Did we ever create another DFA? Yeah, we created this other one. So create a DFA B, since A is already taken, such that the language of B is or such that B accepts strings of length at least something. I can't say 3, because 3 would have been the other scenario. So I'm actually going to copy this one down here. We need a previous step or some assumption. Assume that the number of states in A is like the length k. Nothing's stopping me from doing that, because every DFA has to have some finite number of states. So we're going to be assuming this. Then we create B such that B accepts that k. So greater than or equal to k. Now what's next? Need another creation. So create C such that C accepts what? The intersection. Now we get the copyright between A and B, right? Like the language you're checking, or the machine you're checking if it accepts an infinite language, and the machine that accepts strings of at least the number of states of that original machine. If the intersection is empty, so we'll run C, we'll run the Turing machine on this input C. If T accepts, will we accept 2 or will we reject? What do you think? What does it mean that I accept here or that I reject? If T accepts, that means the intersection is empty. So there's not, so your machine A doesn't accept strings that are bigger than or equal to the number of states. So I never revisit the same state twice. So if D accepts, we're actually going to be rejecting. So something different than before, since we don't have a cell, or since we never revisit the same state twice. However, if it rejects, we're going to be accepting, since that means a loop exists. So our language is infinite. Okay, that's sort of it. Again, let me just draw this machine. So DFAB starts off at Q0, goes like to Q1, and keeps going until it reaches QK. So the number of states of B is actually K plus 1, like K minus 0 plus 1. The reason for that is to ensure that we accept strings of length K. So that if you want to accept a string of length K, your number of states has to be at least K plus 1. And what are the transitions? Well, whatever your alphabet is, E1, E2, like all the way to En, whatever your elements are. If like we're talking the alphabet is this thing. On every arrow, we keep accepting those. And then we self-loop on those two. And the last state has to be accepting. Cool. So that's basically it. Hopefully that made sense. Now for you, you can practice this problem yourself. So let infinite PDA be this language where PDA and the language of M is infinite. So there's actually a solution is on Moodle for this. If it's not posted yet, we'll post it soon. But the idea here is very similar, but like instead of using maybe DFAs, we're using PDAs. And instead of using, if like you ever use a regex, you'd use a CFG here instead. The idea is so similar, it's exactly the same. And even all the problems there already is the same, right? Like we're copying and we're pasting, we're changing just a few parts, the parts that we care about. Like literally here, all we changed was, okay, there are different. I'm not saying they're exactly the same, but if you practice enough, you start seeing patterns, just like with pumping lemma. With enough solving, it's all going to be the same. Except for like maybe a unique problem there or there that needs some head scratching. Like with this problem, it wasn't exactly the same as the first two, right? Okay. So that's decidability. Never enough to solve, right? You could always solve more and more problems. So same idea as before. Okay, moving on to the next idea, which is the decision problem. So what does it want? Is there an algorithm that takes as input a statement written in formal logic and produces a yes or no answer that's always accurate? Let's read it like 10 more times. Is there an algorithm that takes as input a statement written in formal logic and produces a yes or no answer that's always accurate? So in other words, can you write a program, like write some, I don't know, it could be a Java function, a Java program, C++, whatever you want, or just an algorithm like pseudocode or a high-level description. But what I care about is the algorithm that you wrote, if it takes as input something that we wrote in formal logic. Like if I ask the question, is there a number bigger than all numbers? It's like, oh, is there some n0 such that for every other n0 is bigger than those n's? And like we can say such that n0 is not exactly n. Is there something like that? No. we know the answer for that. You can just make some new number n0 plus 1. That's definitely bigger than n0, so like the theorem doesn't work. But there are some other questions that we might ask that are harder, and we care about knowing the answer. So can your algorithm predict yes or no correctly? That's what we care about. Now, there is an answer for this that has to do with lambda calculus, if you've heard of that before, but it is kind of hard to wrap our head around it. But are there some buzzwords on the screen that we've seen before? What do you think? So let me just add here that these maybe belong to the natural numbers. But are there some buzzwords on the screen? Well, I have them kind of circled. Input. Yes, no, it's always accurate. We've talked about this before. It's kind of like a decider in Turing machines, right? What's a decider again in Turing machine? It's a Turing machine. You give it some input, it'll be correctly able to tell you yes or no. So, in other words, we could ask this question in terms of Turing machines. Is there an algorithm that can determine, given the description of a Turing machine and the input from its tape, whether the machine will run forever or it's gonna halt? So, still asking if there's an algorithm. But this algorithm this time is gonna take as inputs what? A Turing machine and its input tape. It's gonna tell you yes if that machine halts, or like stops, and no otherwise. Cool. Now, the answer for that problem is actually no. Like, this is called the halting problem. The problem before was the decision problem. This is kind of like a variation of it. Not a variation, like just another way of asking it. And the answer is actually no. But the interesting part isn't the yes or no. Of course, that's interesting, but how can we prove that it's not the case? We're going to be using contradiction. So let's go ahead and prove that. And the way that contradictions usually go is, hey, we assume that the main problem that we're trying to prove is not possible. We'll assume that it is. So assume that such an algorithm does exist. And like algorithms, when we say like a high-level description of something, it's similar to saying like a Turing machine itself. Like when you have a high-level description, that's the same as if like you have the machine. So we're going to be assuming that this algorithm or this machine exists, and we'll call it H. So H for halt. Now what? This machine is going to take two inputs, a program like another Turing machine, and the input from its tape. And we're asking the question, does the program halt? Your machine H should be able to correctly either say yes or no, like yes, this program will halt on this input or no otherwise. Why are we asking this? Because there's always the danger, there's always the scenario where what if it loops forever? Because as Turing machines are like stronger than DFAs, PDAs, with over there we didn't have to worry about looping. But here there's a possibility that your program might loop forever. So that's why we're asking this question. So when we say yes, it halts, it might mean like your machine either accepted or rejected, or if we say no, that means, oh, it's probably likely going to be looping forever. Now, just like we've been doing all day today and with every other decidable question, we're going to be building on top of this machine. So we assume that H does exist. So it is decidable. It exists. Just like EQDFA, like EDFA, there's nothing stopping you from using it to build a bigger machine. So that's what we're doing. However, the wiring, we're going to be doing them differently. If H accepts, like if H says yes, the program does halt, our machine, we're going to be making it loop forever. Why am I doing this? Well, I want to reach a contradiction. This is just how the steps go, how the construction of proof is going. If it says no, we'll say yes. Then what? We'll make our machine take one input. So kind of like a splitter, it takes one input, then it's going to split them into two different inputs. We'll call this machine C. Now comes the question, what happens when I feed C into itself as input. So we created the machine C, it's perfectly fine. Now what happens when we feed it itself as input? If you're figuring that it's hard to imagine like you just wrote a Java program that takes as input a string, and that string that you feed it, it's the entire program itself. So what happens when C takes itself as input? Well, two scenarios. So we have C here and we have C here. We're asking H, what does C do when it takes itself as input? See, like try to see the inner picture and the outer picture. H is being asked, what does C do when it takes itself as input? That's literally what's happening outside. We made a machine C and it's taking itself as input. Will H be able to predict correctly? Let's check the two scenarios. If H says yes, C does halt on itself, what does C actually do? It's looping forever. So that prediction was wrong. What about the other case? If H predicts that C will not halt on itself, like it will quote-unquote loop forever, what C actually does is output yes and like stops. It does halt. So no matter what H predicts that C will do, it's always predicting it wrong. And that's where the contradiction comes. You assume that you have a machine H. No matter what you give it a program and what input, it'll be able to correctly, like go back to the decision problem. It's gonna always produce yes or no correctly. But is that happening here? No. Okay. Every time H predicts what C is going to do, C actually does the opposite. So when H says, oh, C is going to loop forever, C actually just outputs yes. When H says, oh, it's going to halt, C actually loops forever. So that just means this is not possible. And the halting problem, it doesn't exist. Like we can't, or like is there a machine that will be able to correctly predict other machines, other Turing machines, if they will halt forever or not? The answer is no. Now, maybe to see this in better practice, let's solve a couple of questions. So, consider the language looptm. It's the language that takes two things as input, m and the input w, or like the string w, and it'll tell you yes if m loops on w or not. So like what's the answer for part A? It's literally that. Like what are they asking here? Will m loop forever on the input w or not? Now they're saying show that this is undecidable. We haven't seen this question before. So far, everything we've shown is proof that it is decidable. How can we prove that something is undecidable? Similar approach, we're going to be using contradiction. We're going to be assuming that it is decidable. And just like the Turing machine, that's just like the halting problem, use it to build something, and then we reach a contradiction. But the something that we're going to build is not like a logical paradox or a logical error like what we saw before. It's going to be actually the following. We're going to be proving that this theorem. So what does this theorem say? If A is reducible to B and B is decidable, then A is decidable. This is a theorem that's fine. And this is actually a theorem that maybe we've been using all day long as well. Like usually you'd have a B is decidable. Then you'd use B to build a strong another machine, A, and then you realize that A is decidable. That's literally what we've been doing at the beginning. In other words, it's as if we're saying A is at most as hard as B. Like in terms of complexity, if you were able to solve B, you should be able to solve A because A is at most as hard as B. All you need to know is that A is reducible and that B is decidable. Okay, but how can we use this in terms of contradiction? Well, B, we're going to make it B loop TM. Like we're going to assume that B is loop TM and we're going to say that, loop TM is decidable. Then we're going to use some other machine A that we know is undecidable. Something like halt TM. So the machine that we just proved a second ago is undecidable. If we assume that B is decidable and we're able to reduce A to B, then that means A is decidable. In other words, that means that a whole TM is decidable, and that's where you get a contradiction. You're using loop TM to build a machine that you know is definitely undecidable. So there's whole TM and there's another machine called ATM. So ATM is just the machine that takes as input M and W and tell you yes if M accepts W or not. So it's another language that we know is undecidable. Like, for the sake of this problem and to see like another language, assume that this is given. Assume that ATM is given is undecidable. How can we use loop TM to accept this machine? Or to make this machine decidable? Well, remember the original problem. What happens when I run M on A, where M is a Turing machine? Run M on its input W. Three things. Either M accepts W, which is great. M could reject W, which is also great. The thing that's not great is there is a third scenario. What if M loops on W forever? This is the main reason why whole TM and ATM don't work or are undecidable, because you can't really predict this third part. Like, what if you're running a program for 1,000 years and you decide it's probably looping forever, so you should probably terminate, but no, it needed like 1,000 years and 1 more second or 1 more minute to output its answer. You can never really know if something is looping forever or if it's just taking a really, really long time. However, part A, or this assumption, will help us with that. If we assume that loop TM exists, what does that mean? You have a machine, say we call it R, that decides loop TM. It takes as input M and W. It'll be able to correctly tell you whether yes, M loops on W or not. That solves the issue that we have over there on the right. If I have a machine that'll able to correctly tell me whether a Turing machine loops on a W or not, then that solves this issue that ruins on the decidability for a bunch of other machines. So that's the intuition. We're going to be using this loop TM to build M loops on W, or we're going to build this machine. But loop TM will fix this problem for us, and that's really why it's undecidable. Okay, so let's do that. Just like before, let me get this thing, because even for undecidable problems, again, it's similar stuff. Okay. But here, we'll maybe call it ATM. Why am I calling it ATM? Well, I'm literally using it to build ATM, the Turing machine that I know is undecidable. So on input MW, where M is a Turing machine, and W is a string, or like the input tape, whatever that is. What do we want to do first? Well, let's just use loop TM right away. No need to create like DFAs or Turing machines, things like that. There are ideas for that, but not for now. Just right away run Turing machine R on the input MW such that R decides loop TM. What does that mean? So what should we do if R accepts? If R accepts, that means that M loops on W. So what should we do? Should ATM accept or reject if M loops on W? Well, you reject. So if R accepts, we're going to be rejecting since M loops on W. Like if you know it's looping forever, it's never gonna say yes. That's equivalent to it just it never being in the language. Like if M is looping forever on this input, it's never gonna accept that input. So it might as well reject it. So that's why if R accepts, we're gonna be rejecting. However, now if R rejects, it means it doesn't loop. So what should you do? The loop scenario never happens. So there are only other two scenarios, either M accepts W or M rejects. If you know you're not gonna loop, well, great, just run M on W. The machine M, just run it. And if M accepts, you accept. And if M rejects, you reject too. Like M accepts, that means, oh yes, M does accept the string W. Otherwise, you reject. And here lies the problem. So here is the contradiction part. Why? Think about it. We just made a machine that will be able to decide the language ADM. Now this is the language. Maybe I actually should have kept it X. Since X decides ATM, and we know that ATM is undecidable. And ATM is undecidable. Why is it undecidable? We can do a similar proof to the halting problem to prove why ATM is undecidable. For the sake of this problem, just assume that it is undecidable. So what we did, we created X on input da-da-da. If M loops on W, we reject. Then finally, we just run M on W, and if M accepts, we accept. If M rejects, we reject. This literally decides the ATM machine, which should correctly be able to tell you if M accepts W or not. But that's a contradiction. So what could we conclude from this? Our original assumption is wrong. Loop TM is undecidable. Okay. So I probably should have written this here, that we're assuming that loop TM is decidable. So we were able to reduce ATM to it, which makes us conclude that ATM is decidable, but it actually is not. Contradiction. Great. There. The next two problems are similar, like this one where prove that there's the language where the Turing machine TM accepts ABB, and there's this other one here you could read. We actually never solved them in class, so we're going to be solving them next time. For now, we'll do this part, which we actually did solve in class, but make sure you check part 2 and part 3. Because they're like, if you try to solve them, it'll be helpful for next time. Anyway, the last problem for today, which is 5. And here we're actually going to be proving that ATM is undecidable. So we just assumed that it was not in the previous exercise, but here we're actually going to be proving that it is. Consider the acceptance problem for Turing machines, ATM, where M is a Turing machine that accepts the string W. Show that ATM is Turing recognizable. What does that mean? Show that ATM is Turing recognizable. It's literally just like the recognizer, you know, like we had this discussion before. What is a recognizer? What is a decider? It's just that, like, prove that it is a recognizer. Now, the cool thing about recognizers, you don't care about what happens when I should reject. All you care about is, oh, if I should accept, then I will. And that's easy to do. So we'll say on input MW, step 1, run on W. If M accepts, I accept. And that's enough. This is now a recognizer for ATM. Why? All you care about with the recognizer, it's going to be correctly tell you yes when it should accept. And no, I don't care. I could loop forever. I could maybe actually should reject. I don't care. All I care about is for recognizers, it should be able to correctly tell me yes. And that's what happens here. Does M accept W? We'll run it. If it does accept, you'll accept. We could even actually add this second part where we say, oh, if M rejects, reject. We could add that part, but it doesn't make a difference. It doesn't make it stronger because it's still just a recognizer. Why? Because there's the third scenario that we can't really write, which is what if M loops? We want to say reject, but we can't, right? We can't do that because we don't know, as we saw with the previous exercise. Great, so that's a recognizer. The next part. In showing that ATM is undecidable, we introduced a Turing machine D as follows. Run H, or D, on input M, where M is a Turing machine. Run H on input M with something. If H accepts, reject. If H rejects, accept. So the wiring is opposite. The question is, what is H supposed to be, and what is the missing second component of step 1? Well, let's draw what D is. They're building this big machine D. They're saying it takes as input only M, and inside there's some machine H that takes as input also M, so that the same thing is as if they plugged it and something else that we don't know what it is. And they're saying, oh, if H accepts, we're gonna reject. And if H rejects, we're gonna be accepting. So like the wiring is opposite. Remember that like the whole purpose of this is to prove that ATM is undecidable. So that's why they're building D, and that's why they assumed something that H exists. So what is H supposed to be? It looks very similar to what we did with the halting problem. What is H supposed to be? They used it inside to build a bigger machine D. Now the purpose of D is to prove the contradiction. So what is H? Well, it's your assumption. You assume something and then you build on top of it. So H is actually the machine that decides ATM. Can you see? Are you able to see that? Am I able to see my cursor? There you are. So this actually decides ATM. Okay. Now, what about this part? Like, what's the extra input here? What do you think? Like, you could only use the things that you already see inside, in front of you. Like, I'm either gonna put here. It's this. It's like, again, since it's similar to the Turing machine, this is the halting problem. It's probably also gonna be M2. Remember the whole splitter idea, where like we split the input into two different things? Yeah, that's kind of it. Okay. Now we get to the next part. So like part 2 was only that, asking what is this other thing? It's M, and what is the purpose of H? If you're not completely convinced with this part M, ask yourself, well, what else could I give? Should I give it itself H? Should I give it D? That's maybe like the answer to the next part. Like I could say W, like another input. But then I'd have to wire it to be the splitter, which is just the same thing. Type. A contradiction is arrived by running D on some input. What is that input and what is the contradiction? So what should M be? What should I feed into the machine D to get my input? Now M is just arbitrary, right? Like these three M's, which are all the same, they're arbitrary. They could be anything. What we want to feed them, well, there are two possibilities, either D or H. Like either I feed D itself or I feed it H. If you compare it with what we did before, you probably want to feed it itself, like we fed C itself. But what happens if I feed it H? And remember, H decides ATM. So if I decide to feed it H, okay, then we have H here, and we have H here. And we're asking the H, what does it do when it takes its input when it takes itself as input? No, sorry, not that. We're simply asking H, what does H do when it takes itself as input? But is that really happening? In the small picture, we're asking H, what does H do when it takes itself as input? But that's not really what's happening outside. Outside, what's happening is D is taking H as input. So if H predicts yes, and D says no, doesn't really hurt us. Like, there's no contradiction. Like, okay, D is saying no when it takes H. But that doesn't really relate to what H is saying, right? H is simply saying, oh, if I take myself as input, I'll say no, or I'll say yes. Again, if you're not completely convinced, maybe if we give it D, you'll see there's a more relation, or a better relation. So let me now actually give D input. So now we're asking, what does D do when it takes itself as input? So in the small picture, we're asking H, what does D do when it takes itself as input? Does it accept or does it reject? Remember, H will tell you yes if D accepts D, or no otherwise. So there's a small picture inside and there's a bigger picture outside. Because that's literally what's happening on the outside. D takes itself as input. So we're asking H, will D accept or not? And if H says yes, D does accept. D actually rejects. If H predicts that D will reject itself as input, D actually accepts. So what H is predicting inside is the opposite of what's actually happening outside, and that's why we get the contradiction here. So hopefully that made some sense. It's very similar to what we did with the halting problem, like a logical paradox. Okay, great. That's kind of it for today. And again, we can always solve more and more undecidable problems. It's never enough, so just as much as you can, keep practicing these ideas. But you'll notice something, that for undecidable problems, we're kind of doing the same thing as before. Like, we're building on top of blocks, but the difference, unlike before where we were building on top of something that we know is decidable, here we're assuming that something is decidable, like what we did here. We're assuming that loop TM is decidable, then we build on top of it, and like the whole thing breaks down. Because what you assumed, what you're building on top of, that's not true. Okay, so that's going to be it. Actually, if you're interested, you can learn about more on Alan Turing, the person who made the Turing machines, and you can learn more about Turing machines and the halting problem in this video. It's really interesting. I really advise you to check it out. So, some really cool stuff over here. Okay, I'll see you in the next one.